Welcome to Experiment 4A, where we explore the cutting edge of wirelessly powering energy-neutral devices. How to perform wireless power to energy-neutral devices. In Reindeer, we have investigated the use of distributed antennas surrounding its users to perform, among other things, wireless power transfer over RF. A bit like RFID on steroids. To do this, Techtile was constructed. Techtile is a research testbed developed at KU Leuven, designed for exploring advanced technologies related to communication, positioning, sensing, and wireless power transfer. This platform is part of the effort to develop future wireless systems, such as 6G, which will integrate not only communication but also distributed sensing, deep edge computing, and federated learning. The testbed provides an environment for experimental research on hyperconnected spaces, enabling scientists to test and validate new wireless connectivity and sensing solutions. Techtile's infrastructure includes 140 interconnected tiles, which contain various sensors and processors, such as Raspberry Pi devices, allowing researchers to study acoustic, RF, and optical strategies. The system also supports advanced synchronization and power solutions, such as Power over Ethernet, making it a versatile tool for next-generation technology development. Each tile in the Techtile infrastructure consists of several key components designed to support distributed wireless power transfer. A Raspberry Pi 4 to do local computing, connected to the Techtile server for central processing. A software-defined radio, each equipped with 2 antennas, giving a total of 280 antennas in the infrastructure. How to study the energy transfer efficiency of such systems. In the Reindeer project, we have investigated devices with different capabilities, where a special case is energy-neutral devices. These devices have only a very limited power storage on board to provide power for a single operation. Consequently, they require an external source to supply them with power to operate. The efficiency of the wireless power transfer is here studied by investigating both the RF and DC energy. The RF energy is recorded by a spectrum analyzer to measure how much power is received at a specific location in the Techtile room. Depending on the location and the transmitted signals, the amplitude of the signal will vary. On the other hand, in time it could look like this. But what about DC energy? Energy-neutral devices need a DC power source, so the RF or AC power must be converted to usable DC power. The electronic component responsible for this conversion is typically called an energy harvester. The amount of available DC power in energy-neutral or battery-less devices will therefore depend on the waveform, power level, and design of the energy harvester. In following experiments, the energy harvester or RF/DC converter of NXP is used. As shown in, the harvester's efficiency is optimal at a certain input power level. Our solution, measuring the available DC energy with an energy profiler. To achieve precise DC power measurements that account for nonlinearities and threshold voltage levels, we developed an energy profiler. The EP includes a tuning network to improve impedance matching with the antenna and integrates precise power measurement capabilities through a programmable potentiometer and a high-resolution 16-bit analog-to-digital converter. This configuration enables accurate power level monitoring, essential for assessing energy harvesting efficiency. Additionally, the EP offers an adjustable target voltage feature, allowing users to simulate real-world conditions accurately. This flexibility is critical, as microcontrollers typically require a minimum input voltage of around 1.8 volt for stable operation. By adjusting the target voltage, the EP can effectively simulate various operating conditions to validate performance across different scenarios. But how to get the power at the END? Different strategies are investigated in Reindeer to perform wireless power transfer via RF. Each of those strategies have different synchronization requirements and achievable performance. We use random phase sweeping when the system is not phase coherent, but provides frequency synchronization to illuminate dead spots. By randomly changing the phase of all transmit antennas at regular intervals, fluctuations in the received power can be induced, yielding different levels of constructive interference at different time and spatial instances. This is especially interesting when the average received power is below the required threshold for a device to get charged. In the other hand, we have codebook-based transmission. A feedback mechanism can be used to apply different phases to the transmit antennas, where the energy-neutral device can respond to the best set of applied phases. Other option is geometry-based, where knowing the geometry of the antennas, environment and position of the energy-neutral device, geometry-based techniques can be used to focus energy to the END. Specular reflections and scatters can be modeled based on the information of the environment and used to estimate the channels between the END and the infrastructure antennas. And finally, there is reciprocity-based. In a reciprocity-based setup, the device sends a pilot. This pilot is received by all antennas and the received phase of the signal is recorded. This received phase depends on the distance between the device and each antenna, as well as the environment. For instance, signals can be reflected or obstructed. In the next step, the infrastructure transmits a signal with the opposite phase than that was received, in order to constructively combine the signals at the device. But what have we obtained with all of this? The following experiments are conducted using the ceiling tiles of the Techtile testbed. 1. The phase sweeping. Without prior knowledge on the position of the energy-neutral device or channel state information, distributed beamforming cannot be used. To still supply a sufficient amount of energy to a device, phase sweeping is proposed as a suitable approach for delivering this initial energy. All transmitters in this setup are frequency synchronized and configured to transmit a single carrier at 920 MHz. The phases of each transmitter are periodically adjusted every 5 seconds. In this example, the infrastructure transmits RF power at 32.5 dBm. This energy is received as low power, enough for initial access by the device. As shown here, DC power levels vary every 5 seconds. Though low, only a few microwatts, these levels are adequate for initial operation. Correspondingly, the voltage fluctuates over time. This illustrates that the harvested voltages exceed the 1.8 volt threshold and that a microcontroller can be booted effectively, if also the incoming power is sufficient and exceeds the microcontroller's power consumption. 2. Different WPT strategies. When having information regarding the position of all antennas and the target device or by using a pilot signal, we can beamform energy towards the intended device. When sampling the received energy in a 2D plane, the created power spot is revealed. Different strategies are explored such as geometry-based beamforming using line-of-sight, first-order reflections and second-order reflections together with reciprocity-based beamforming. These first results shows that the geometry-based schemes are promising, but multiple-order reflections need to be considered to improve the accuracy and total power. In conclusion, within the Reindeer project, we have investigated different strategies to power energy-neutral devices wirelessly over RF. Several of them were experimentally validated in the Techtile testbed. We have demonstrated that random phase sweeping can be an appropriate approach to provide initial energy to ENDs. After this, a pilot can be sent to improve the wireless power transfer efficiency using reciprocity-based beamforming. In addition, we have also showcased that geometry-based techniques where we know the environment and the position of the device can be used to provide energy wirelessly.